Hi, I'm going to make the first part of the exam. That's the theoretical part. I'm going to start with question A that says, which due to decrease the speed of a wave traveling on a string to half its current value by changing the tension in the string. By what factor must you decrease the tension in the string? Well, as we know, we have the first equation, and the first velocity equals the square root of force over um, the linear density. And we have the second velocity that should be half, if I'm not wrong, to decrease the speed of the wave traveling on the string. But it's half, so it's gonna be um, 1/2 of velocity 1. So we need to find by which factor do we have to increase the to decrease the force in the first velocity. So if we do this, we're gonna have that velocity 2 equals 1/2 of velocity 1, which velocity 1 in terms of force, here, which this is gonna be the force 2, if we guess that is the first one, the first tension, over the linear density, that this doesn't change. So we're gonna have that 1/2 of velocity 1 squared times mu equals the second force. But here we have that velocity 1 equals the square root of f1 over u. So what we're gonna do is not really. Wait, first we have this, so we're gonna equals this 2. That's gonna be 1/2 of the square root of f1 over the linear density, that equals the square root of f2 over mu, right? So if all these we put to the square, we eliminate this, and we obtain that 1/4, as we have this half in to the square is going to be 1/4 of f1 over mu equals f2 over mu. So we can just forget about the linear density, and we can say that the contention we need is going to be equals to 1/4 of the first tension. Now, for question B. For question B, it says, the different colors of light we perceive are a result of the varying frequencies and wavelengths of the electromagnetic radiation. infrared radiation has lower frequencies than does visible light, and ultraviolet radiation and ultraviolet radiation has higher frequencies than visible light does. The primary colors are red, yellow, and blue. Order these colors by their wavelength, shortest to longest. So we have red, yellow, and blue. The three colors. So its frequencies. This is a smaller. That the red frequency is smaller than the yellow frequency than the blue frequency. And we have the speed of light when talking about color is lambda times the frequency. So according to this, to a so behind this we have that the churches how you say wavelengths are gonna be blue, then yellow, and at the last red. This is gonna be like this, then it's gonna be like this, and red, well, something like that, you know. So we have this blue, yellow, and red. Because as we know, the frequency, okay, they are asking for the wavelength. We know that the frequency is the inverse of the wavelength. So then, if this is the biggest frequency, this is gonna be the shortest lambda. You know, we're gonna change this. So this is the red one, the yellow one, and the blue one. That's how we know this one. Okay, for C, I mean it's like you see. Oh my gosh. For C, we have you stand on the curb waiting to cross the street. Suddenly you hear the sound of a horn from a car approaching you at a constant speed. You hear a frequency of 80 Hz. So it is approaching. When it is approaching you of 80 Hz. Okay. After the car passes, so when you're here, when it goes, you hear frequency 72 Hz. Okay? So here it is. When it's approaching you, you're here in this point. You hear 80 Hz. When going, you hear 72 Hz. And it wants you to know the speed. So I'm gonna erase this, or not, maybe not. I'm gonna just wait. We know that the formula, you know, the frequency in general, also will be, as this is actually a kind of long exercise. So we have the formula for that says that this frequency equals the frequency times the velocity of sound. And as you are not moving, we don't need the the velocity of the observer as it is 0, so we're not gonna add it or subtract it from the equation. We're just gonna ignore it because it is 0, as I've said. So the velocity of sound over the velocity of sound plus or minus, depending on if it is approaching or if it is getting away from you, of the source. Well, actually here's the velocity of sound on air. That the velocity of sound on air is gonna be 343, if I'm not wrong. Yeah, 343 meters per second. So if I calculate it, and of the source. The source is gonna be the car in this case. So here's plus or minus. I'm going to use the minus because it's when it is approaching to you, and we have also this equation. It's exactly the same, just that with a plus. Oh my gosh, sign, right? And it is when it's getting away from you. So as we have this, just what we want is this velocity, and this and this velocity, it's exactly the same. Okay? Because well, it's a constant. It's the same for both of them. This is gonna be this F1, and this F2. It's gonna be the 80 and the 72. So we're gonna have, if we evaluate, we're gonna have that 72. Which one is 72? This is 80. 80 times BA minus BS over BA equals, I'm gonna write it here down, but this is an equals 72 BA plus the BS over BA. So we can say goodbye to these ones, and we're gonna have that 80 BA minus 72 BA equals 72 BS minus 80 BS. Okay? So what we want is these two, is the BS, so we're gonna have it as a constant. With the BS is gonna be we can also take away the velocity of sound on the earth, as we have seen, is 343 meters per second. So we're gonna have 343 this multiplied by 80 minus 72 over 72 minus 80. Oh, oops. Oh no, but as here's in negative, and I forget that. Negative goes as positive, so they sum. So it's 80 plus 72. Sorry, yeah, that's right. So we're gonna have, we redo that. That this is something like 80 meters per second. Basically, that's all you have for problem C.